So now, first thing I'm going to do is kind of show you guys the course, chapter 6 module, how that's going to look, because last time we met, it wasn't ready, and now it's ready. So we're going to do that first. I'm going to share my screen. There we go. So here's the course. We know what this looks like. I showed it to you previously. Many of you got here possibly by clicking on this link to get to the period 2 class. Now, as you can see, the calendar is starting to be populated with things that I've been doing. Obviously, the Tuesday, Wednesday stuff is for the periods 1 through 5 classes that you're not a part of. You'll be looking primarily at the Thursday, Friday stuff. I've already started to add things to this. This is the presentation that I will be doing today in class. It's already linked. It is a PDF version, not the PowerPoint version. And these are them. This is the chapter 6 module. All right, I want to look at this as a whole page because it's easier to see. So I'm going to click into the modules. And we're going to switch to what you guys can see. So first thing here, at the very top of the modules, and you saw it on the previous page as well, we have the formula sheet and tables. All right, this contains the formulas that you'll be allowed to, that will be provided to you when you take the AP exam, and also table A. Yeah, so this will be useful. We will be needing to use things such as table A moving forward in section 6.1 in chapter 6, and obviously in future chapters. And some of these formulas will be useful. This formula sheet does not contain all the formulas that you have used in this class, but it contains some of the more important ones. Other ones you're just going to have to remember. Chapter 6, there are 3 sections in chapter 6. We're starting with 6.1 today. We're going to do the lesson for 6.1 today. We will get through the entire lesson. And then tomorrow we will do practice problems for section 6.1 in a class during our live time. Excuse me. If you check out the class notes and resources, I have this kind of broken up into categories. We have notes. All right, here again is the presentation that we'll be doing today for section 6.1. I also have a study guide, which is kind of pre-made notes. All right. This is the study guide for chapter or section 6.1, discrete and continuous random variables. All right. Goes through some examples. We have some definitions. Right. Many of these things you will see today in class. This is just kind of a preset set of notes or study guide with some definitions, examples, formulas, and things like that. That is just meant to be a resource for you guys. All right. So there's that. You'll have that available. All right, you also have the AP Daily videos linked here. When you click on these links, you might have to log into your AP Classroom to access the videos. Once you do that, they should just pop up and play. There's also examples from the textbook. These are links to videos. Most of the videos for the textbook examples are like 3 minutes long, 2 minutes long. They're very quick. And then there is some calculator instructions here. Section 6.1 has some calculator instructions for inputting and analyzing random variables in the calculator, which could be helpful. It, can save time if we're trying to find the mean or standard deviation of a random variable. This could help. All right, so we have that available in our notes and resources. And then the other thing that's included in each of the sections is the practice problems and solutions. Up here we have the problems, down here we have the solutions. The practice problems is just a set of problems that I've selected from the textbook in the exercises section of section 6.1, designed to help you practice the math that we're learning in this section. It's just the problems. You don't have to go find them in your textbook or do problem this, and that, right? These are not required. It's not homework. This is an opportunity for you to practice. I suggest that you do them because I think doing the problems will help you understand the content. However, it will not be checked. It will not be required that you submit them. It is an opportunity to practice. All right. Once you've tried to do the problems, you can look at how is this possible. Sorry, people are just having issues getting into the meetings, and I don't know why they can't get in. All right. So we have our practice problems and solutions are here. So once you've attempted the problems, you can check to see if you've done them properly, right? Because that's always nice to know. Did we do the right stuff? That's helpful, right? So each section has problems and solutions, okay? So that is the general idea of how the modules will be set up, okay? Yeah. Another person joining. All right, guys, give me a minute. I have a student who can't get into our class, and I'm not entirely sure why. Let's see. Okay. People who can't access the meeting. That's annoying. All right. All right, moving forward. So that's what these things look like, guys. I do have the Chapter 6 multiple choice assessment available. This is based on all 3 sections. So I suggest doing it once you're comfortable with the 3 sections. I'll be adding the free response question assessment later, hopefully either today or tomorrow, at the latest, maybe on Monday. All right, so then that will be everything for Chapter 6. All right. Is there any questions?
So do we have homework?
No. Short answer is no. There's practice opportunities. We'll do practice problems in class like tomorrow. That's what tomorrow's in class time will be spent on. The only things that you are required to submit through like Canvas and things are the assessments. Yeah. I think you guys are already trying to manage enough on your own time right now with your 5 other classes besides mine. I'm trying not to add any more stress to you guys. I know this is an AP class and we will be covering a lot of content and there will be a lot that we need to learn, which is why I have resources and opportunities for you to practice. But I'm not trying to add more stress than you guys are already under. So that's the long answer. So yeah, any other questions? Okay, so then what we're going to do next is get into our lessons. So if you are taking notes, which you should be, I recommend that you do. That really helps in the learning process. Please get out your notebook or paper or a pencil, pen, whatever you like to write with and write on. Have that ready. We're going to have some notes. Go get this going. Give me a second. There we go. Excellent. So here we are at the beginning of chapter 6 on random variables. We're doing section 6.1 today on discrete and continuous random variables. Right. And this is from our textbook, Practice of Statistics, blah, blah, blah. So here we go. In this lesson, you will hopefully learn how to compute probabilities using the probability distribution of a discrete random variable, calculate and interpret the mean expected value. Mean and expected value become interchangeable terms. They're referring to the same thing of a discrete random variable. Calculate and interpret the standard deviation of a discrete random variable, and compute probabilities using the probability distribution of certain continuous random variables. We will see some examples of these things today during the lesson. All right. So here we go. First, random variables and probability distributions. A probability model describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. Right. Consider tossing a fair coin 3 times. We will define the random variable x, that is a capitalized letter x, to be the number of heads obtained. So we flip a coin 3 times. X contains the value of how many heads we had. All right. When we flip a coin 3 times, we have these possible outcomes. Right. X will have the value of 0 if there are no heads, meaning we flip 3 tails. X can equal 1. Head shows up once. The order in which the head shows up matters, which is why we have head showing up first, head showing up second, head showing up third as 3 different events. X equals 2 if we get 2 heads. All right. And x equals 3 if we get 3 heads. All right. So there's 4 possible values that x could be: 0, 1, 2, or 3. Okay. So we can represent this in a table where the value of x can be the top row and the probability of each of those things occurring, of x having each of those values, is the bottom row. There's only one way to have it have a value of 0. There's 3 out of 8 ways for 1, 3 out of 8 for 2, 1 out of 8 for 3. And again, just with like other probabilities, these probabilities must add up to 1. Right? Can't be more, can't be less, or else we forgot something. We can also display this probability distribution in a histogram. And just like when we display quantitative data, we can use a histogram to represent the frequency in which these things occur. Right? In this case, instead of frequency, we have probability. Right? So we can have 0 show up 1/8 of the time, 1 out of 8 times, 3 out of 8, 3 out of 8, 1 out of 8. Right? We get this nice symmetric histogram. So these are ways we can show the distribution of a discrete random variable. Right? A random variable takes numerical values that describe the outcomes of some chance process. The probability distribution of a random variable gives its possible values and their probabilities. All right. So the random variable x can have the values 0, 1, 2, or 3. Right? And then the distribution is the table or the histogram. If you would like another moment to write anything down, please raise your hand. Use the little raise your hand icon if you need a moment to write. All right, I see no hands. So we're gonna move on. All right, there are 2 main types of random variables: discrete and continuous. All right, first we're going to talk about is discrete. If we can find a way to list all possible outcomes for a random variable and assign probabilities to each one, we have a discrete random variable. All right, here's our fun definition here. A discrete random variable x takes a fixed set of possible values with gaps between, meaning it's countable. Right? there's a gap between 0 and 1. There's other numbers that exist there, but they're not possibilities for this random variable. The probability distribution of a discrete random variable x lists the values x sub I and the probabilities p sub I. The subscript I is just a placeholder where it gets replaced with a number, and that number indicates the order in which that number occurred, essentially. So if we look at value here, and it says x sub 1, x sub 2, x sub 3, x sub 1 just means this is the first possible value for x. Sub 2, this is the second possible value for x. It's a way for us to name and record these values when we don't know what they are, right? This is just a general way of writing this. We're not considering a specific example, so we don't have values. This would be the third possible value. And we have to have these subscripts because these values are not the same. I can't just write x, x, x. If I have the same x in those three places, it implies that it's the same exact value each time. It's not, which is why we have the subscripts. Same thing with the probabilities. This is the probability of the first outcome occurring, probability of the second outcome, probability of the third outcome, and so on. And we can continue this list until we run out of outcomes and probabilities. And again, it has to be p sub 1, p sub 2, p sub 3, because these may not be the same probabilities. The probabilities p sub I must satisfy two requirements. Every probability p sub I is a number between 0 and 1, just as other probability things we've considered previously. And the sum of the probabilities is 1. We cannot have a sum greater than 1. Cannot have a probability greater than 100%. Okay? To find the probability of any event, add the probabilities p sub I of the particular values x sub I that make up the event. All right. So what that means is, like in the previous slide, we saw the example of flipping the coin 3 times. If I wanted to know what's the probability of getting 2 or more heads, right, which means I can have 2 or 3 to fulfill that event, then I would add the probability of getting 2 heads to the probability of getting 3 heads. So we have the 3 8s plus 1 8, we have 4 8s, we have a 50% chance of getting 2 or more heads. Right, so we just add those probabilities. So any questions on this slide, or do you need more time to write anything down? Okay. The mean or expected value of a discrete or random variable. When analyzing discrete random variables, we follow the same strategy we used with quantitative data. We're going to describe shape, center, and spread, and identify outliers. Right. The mean of any discrete random variable is an average of the possible outcomes, with each outcome weighted by its probability. Right. When we were considering quantitative data previously, we were typically looking at situations where each outcome was equally likely. So we didn't have to account for the fact that some outcomes had a higher probability of occurring than others. Now we have to take that into consideration, which is why each outcome is weighted by its probability. Suppose that x is a discrete or random variable whose probability distribution is, the table, we have our value and our probabilities. To find the mean or expected value of x, you need to multiply each possible value by its probability, then add all the products. Right, so you'll take first outcome times its probability plus the second outcome times its probability plus the third outcome times its probability, and so on until you run out. In the general formula, it looks like this. We have mu sub x, so we're using mu again, which we did previously with quantitative data. And it's the mu of random variable x, which is why we use the little subscript x, equals the expected value of x. Right, that's what this notation means. We can use these two things interchangeably if we want to. We don't need to list them both each time. We can just say mu sub x or e parentheses x. Those work interchangeably in this case. And again, first outcome times its probability plus second outcome times its probability plus third outcome times its probability, and so on. Shorthand notation, we can use the sigma notation, which is summation. If you haven't seen this before, it is the Greek capital letter sigma, and it means add up all the possible things here, x sub I, p sub I. Technically, you should have some stuff on the bottom and the top here, but that's a whole different story about proper notation. They did not include it, and that's another thing. So, shorthand notation, this means this in shorthand. All right. And can you please raise your hand if you need a minute to write anything down? Okay. All right, so let's look at an example. A baby's APGAR score is the sum of the ratings on each of 5 scales, which gives a whole number value from 0 to 10. Let X equal the APGAR score of a randomly selected newborn. Right, here's our probability distribution. We have values possible of from 0 to 10, and then we have the probabilities of each of those outcomes. All right. Compute the mean of the random variable x, interpret this value in context. So in this example, we see that 1 in every 1,000 babies would have an APGAR score of 0, 6 in every 1,000 would have an APGAR score of 1, and so on. So the mean or expected value of x is given by this formula. Again, we have that mu sub x equals the expected value of x equals the summation of x sub I times p sub I, which we can represent with the math 0 times 0.001 plus 1 times 0.006 plus 2 times the probability of that plus on and on down the line until we get to the last one, 10 times the probability of 10 occurring, which is 0.053, and we ultimately get 8.128. All right. So what does that mean? So the mean APGAR score of a randomly selected newborn is 8.128. This is the average APGAR score of many, many randomly chosen babies. So if we were to just randomly choose babies, do a bunch of choosings of babies, we would eventually get an average APGAR score of 8.128 over many, many trials, essentially. Right? In other words, and that's why we say the expected value, we would expect that if we randomly select a child that the APGAR score is going to be around an 8. Okay. Any questions? Anything I can clarify here? All right. Does anyone need a moment to write anything down? Okie dokie. So since we use the mean as the measure of center for a discrete random variable, we use standard deviation as our measure of spread. Right? The definition of the variance of a random variable is similar to the definition of the variance of a set of quantitative data. If you remember how we calculate the variance in quantitative data, it's the squared difference from the mean of all the observations. We add all those together, right? In this case, suppose that x is a discrete random variable whose probability distribution is given with the table of values and probabilities, and that the mu of x, or mean, right, is the mean of x. The variance of x is this craziness. We can write this as var x if we want. Variance of x equals sigma sub x squared, which again is our shorthand notation. This is lowercase sigma, this is uppercase sigma, equals the difference, right, between the first outcome minus the mean squared times the probability of the first outcome. So again, we have that accounting for the fact that these are not all equally likely. There are unique probabilities to each outcome, right? Plus the difference between second outcome minus the mean squared times probability, so on and so on until we run out of outcomes. And shorthand wise, we can write this as the summation of all outcomes minus the mean squared times their probabilities. Right? To get the standard deviation of a random variable, just like getting the standard deviation of quantitative data, you have to take the square root of the variance. So all the legwork is in calculating the variance, and then you just throw that under a square root sign and hit enter on your calculator, and you then have the standard deviation. All right. And we'll see an example of this on the next slide. Does anyone need a moment to write anything down? Alrighty. So again, we're looking at the same example as previously with the baby's APGAR score. All right, we have our probability distribution, and we're going to compute and interpret the standard deviation of the random variable x. All right, our formula for the variance of x is given as we saw on the previous slide. So to find the variance, we have the first observation, or the first outcome, minus the mean squared times that probability, plus 1 minus the mean squared times probability of getting 1, and so on down the line until we get to the last possibility, 10 minus 8.128 squared times 0.053, which ultimately gets us the variance of 2.066. But again, we're not done. We've only found the variance. We need the standard deviation. Right, the standard deviation of x is sigma sub x equaling the square root of 2.066, or the variance, which is about 1.437. Right. This means that a randomly selected baby's APGAR score will typically differ from the mean. So if we randomly select a baby, the score should typically differ from the mean by about 1.4 units. All right. It's always good to kind of pop the mean back in here when you write your description of, of this, saying a randomly selected baby's APGAR score will typically differ from the mean, 8.128. Just to be more specific, you want to give as much details in your descriptions as possible. By about 1.4 units, it's important to include the word about here. We have rounded the answer. You need to say that it is about 1.4 units, approximately, roughly, something in that terms. Unless you have an exact answer, like this happens to work out to be equal to exactly 1.4, you can say by 1.4 units. But again, it's probably better to keep it a little more general, because not everyone will differ from the mean by exactly that amount. Any questions about this example? Okay. So the next, we've talked about discrete. Now we're going to talk about continuous random variables. Right? Discrete random variables commonly arise from situations that involve counting something. Right? Situations that involve measuring something often result in a continuous random variable. Right? Essentially, this means that the possibilities for our random variable are any of the values between a set of things. Right? When we're measuring a set of people's height, it can go from a really low number to a really high number, and every possibility in between. It's not just normal counting numbers. So a continuous random variable x takes on all values in an interval of numbers. The probability distribution of x is described by a density curve. Probability of any event is the area under the density curve and above the values of x that make up the event. So essentially we're using the same strategy with continuous random variables as we did with the normal distribution and the normal curve in the previous chapter. All right. So remember in chapter 5, we're dealing with probability and we're looking at the normal curve, right? We used the density curve and the area under the curve to find probabilities, and we used table A, z-scores, all that stuff. It's coming back. So the probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of x. That's discrete. All right. Continuous random variable y has infinitely many possible values. All right. Small example of this. If we just look at the interval between 0 and 1, no matter what number, what decimal you give me, I can give you a number bigger than that and smaller than that. And then I can give you another number bigger than those and smaller than those and bigger than those and smaller than those. And I will never get to exactly 0 and never get to exactly 1. I can always find a number less than 1 but bigger than the number you gave me. I can just add an extra decimal place. And there's proofs to show that there's infinitely many numbers and possibilities between 0 and 1, but that's beyond the scope of this course. So all continuous probability models assign probability 0 to every individual outcome. Right? And this is because if we look at the density curve, and if we just draw a horizontal line, right, or not a horizontal, a vertical line, gotta get my terms correct, a vertical line has no width. Because it has no width, it has no area, so it has no probability. Only intervals of values have positive probability, right? Because then we have a width. Is there any questions about this so far? Okay. Does anyone need a moment to write anything down? Okay. So next, let's look at an example. The heights of young women closely follow the normal distribution with mean mu equals 64 inches and standard deviation sigma equals 2.7 inches. We're going to choose one young woman at random, and we're going to record her height as y. Right? That's the random variable y. This is our continuous random variable. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all young women. We're going to answer the question, what's the probability that the chosen woman is between 68 and 70 inches tall? So we go over here. Here's our setup again. State the distribution and the values of interest. The height y of a randomly chosen young woman has the distribution normal with a mean of 64, standard deviation of 2.7. Remember, this is our notation to, like, say, shorthand-wise. We have a normal distribution, and these are the mean and standard deviation. That's the information we need. We can draw a graph. We can figure out things with just this information. We want to find the probability that y is greater than or equal to 68, but less than or equal to 70. Okay. Step 2, we got to do work. To do that, we need to standardize the scores for the two boundary variables, or boundary values, blah, blah, blah. All right, so we'll do 68 first. Z equals 68 minus the mean of 64 divided by the standard deviation of 2.7. That puts us at 1.48. And the upper bound, Z equals 70 minus 64 divided by 2.7 equals 2.22. All right, so now it is usually helpful to kind of look and see what this looks like on our curve, because it helps us identify if we've done calculations correctly, right? So I'm going to do a quick sketch here. Let's use that color. Hopefully this isn't totally janky, but we'll try our best. Right. So we have a give or take normal curve. All right, our mean will be in the middle. We have 1, 2, 3 standard deviations to the right. 1, 2, 3 to the left. Right. And we have a z-score of 1.48, which might be right about here, right? And that's our lower bound. Our upper bound is at 2.22, maybe about here. So the area we're looking for is just the area in here. Right? And this is the same as what we've done previously in chapter 5 with normal curves, right? Remember, when we look up these values on table A, the proportion that it gives us is the proportion to the left of that number and all of it. So when we look this up on table A, when we find 1.48, that's the proportion to the left of 1.48. That's all of this, which I honestly don't need any of it, right? I don't need any of this probability, right? We'll also find the proportion that's to the left of 2.22, right? I only need this part. So I will take the probability of z being 2.22, or being less than or equal to 2.22, and subtract the probability of z being less than or equal to 1.48. And that will give me the section I need. Okay, so when we do this, right, we get probability of z being greater than or equal to 1.48 and less than or equal to 2.22, our shaded area, is the same as the probability of z being less than or equal to 2.22, this whole thing, minus z being less than or equal to 1.48, that part. And when we look these up on table A, we get 0.9868 minus 0.9306, and we get a probability of 0.0562. All right. So this means the probability of randomly choosing a young woman whose height is between 68 and 70 inches is about 5.6%. All right. What questions do you have? Okay. Does anyone need a moment to write anything down from this slide or from a previous slide? I can go backwards. All right. And then that's it. That is the gist of section 6.1. All right. We're doing probabilities using probability distribution of discrete random variable. That was at the very beginning. We can calculate the mean and interpret what it might be in context. We can find a standard deviation. Both of these are with discrete random variables. And we can compute probabilities using probability distribution of certain continuous random variables. All right, continuous random variables kind of make us use what we used for normal curves and normal distributions. All right. Is there any questions on what we've just covered for section 6.1? I suppose not. All right, maybe I'm just that good. So we go end our slideshow. Stop sharing your screen. All right, so with that, that is the lesson for section 6.1. Tomorrow in class, we will do an activity where I'm going to put you guys in like breakout rooms. You guys can work together and work on some practice problems. These practice problems will be similar to the practice problems that I have available in the Chapter 6 module for Section 6.1, but they are different problems. They are also from the textbook. And it's just designed to let you guys have an opportunity to look at other problems and get help if you need it when you're working on those problems, and to work together. Yeah, so we'll get a practice opportunity tomorrow, and then next week we'll move on to Section 6.2, and that should be super fantastic. All right. And if you have no questions, if you're satisfied with what you've gotten today, you guys are now free to go. Enjoy the rest of your Thursday, and remember, we meet again tomorrow. Same bat time, same bat channel. All right, have a lovely day, and I'll see you guys tomorrow.